So I'm going to discuss a long-standing puzzle about ADS-TFT. So remember, the basic idea of the duality is the following. So in D dimensions, you have a manifold M in which you want to do a CFT. And today will be in Euclidean signature. So for example, you might like to calculate the partition function of M. And the duality says that you calculate the partition function of M by summing over contributions of all manifolds X with boundary M. And for each such X, you then do the usual path integral over metrics and other variables on M. Now, this works fine as long as M is connected, but there's a puzzle as soon as M is not connected. So here's a simple picture where the boundary is the union of two components, M and M prime, two disjoint components. X is connected, but the boundary isn't connected. So it looks like it's trying to calculate a connected correlator between the partition functions on the two manifolds, where the sub C subscript means this is the connected correlator of those two quantities. Now, something a little like that makes sense in Lorentz signature, where two wave functions can be entangled. But in Euclidean signature, we're just discussing numbers. So naively, this is the connected correlator of two numbers, which doesn't seem to make much sense. So that's the basic puzzle. Now, there was a new light a few years ago by Saad, Schlenker, and Stanford. They studied JT gravity. It's a two-dimensional theory. So the boundary theory would be one-dimensional, just a quantum mechanical system that you describe by Hamiltonian. They found that the dual was really not a particular quantum mechanical system, but a random matrix ensemble. So this has led many to speculate that maybe in examples of the duality in higher dimensions that are derived from ADS-TFT, it's also true that the boundary is really an ensemble, and that's what the duality is telling us. Sorry, that's what the disconnected contributions are telling us. But I'm not aware where anybody's actually made this proposal in print. And if nobody has, there's an obvious reason for that, which is that there's an obvious problem. Which is that there are many known examples of the duality where there is no ensemble. So, in examples of this duality that come from string/M theory, there's no ensemble. When I say there's no ensemble, what this even means is the following. These theories all depend on at least one integer parameter n, where Newton's constant is a negative power of n. And sometimes there's more than one integer, or sometimes there are some real parameters as well. But anyway, in many examples of the duality, all the parameters that the model has consistent with its symmetries are known, or are strongly believed to be known. And the bulk theory depends on all of the same parameters. For example, well, two of Juan's original examples were ADS4 times S7, ADS7 times S4. In those two examples, there's just one integer n, no other parameter. And n can be measured in bulk since it controls Newton's constant. It's also a flux integral in the sphere. So a bulk observer who measures n knows what the boundary theory is supposed to be, so there's no ensemble. So the fact that an ensemble doesn't exist is one obvious problem with claiming that disconnected contributions when I say disconnected contributions, I mean contributions with disconnected boundary but connected bulk would be interpreted in terms of ensemble average. There simply is no ensemble in the most interesting examples. So I should have mentioned that I'm describing work with a co-author, Jean-Marc Schlenker, who helped with the statement about hyperbolic geometry. The papers in the arXiv as of a few weeks ago. So today I'm going to sharpen the puzzle. Well, two parts of the talk. In part one, I'll sharpen the puzzle. I describe observables that do not get wormhole contributions. That's part one in the talk. So by describing a large set of observables that don't get wormhole contributions, so in other words, they show no sign of apparent ensemble averaging. So if you ask what these observables will be, I'll describe it in more detail in a moment. But I can quickly, I'll say either of two statements. There are observables that involve states that are not black holes. So the language we used in the paper was that there are sub-threshold observables, observables that only involve states below the black hole threshold. So therefore, I'll explain in a precise sense, well, evidence for the statements, that an observable that doesn't involve black holes sees no sign of ensemble averaging, so that the ensemble averaging only affects observables that do involve black holes. But another statement is that the observables that don't show any ensemble averaging are the ones accessible by integrability. So not all examples of ADS-CFT are integrable for large N, but there are important examples of ADS-CFT duality, which involve models that are integrable for large N. What's accessible by integrability is not all observables in those theories, only some observables. I claim that the observables accessible by integrability are precisely the ones that are not affected by ensemble averaging. Integrability does not let you access black holes. Black hole physics is chaotic, which is the antithesis of integrability.
Integrability, you mean integrable underworld.
Yes. So, in space-time, every large N theory is a free theory at n equals infinity. They're all space-time integrable. But the world sheet theory, for n equals 4, for example, is integral in the large N limit. So there's a large class of observables that are governed accessible by integrability, where there are exact formulas as a function of g squared n in some cases. Well, in principle for all cases, but many cases, but in practice for some cases. So I claim that precisely the observables accessible by integrability are not affected by any apparent ensemble averaging. So people studying integrability who feel they're studying a definite theory are correct. Yes?
C or not C, here you mean in the large N limit.
This is not only a statement about the large N limit. There are no, I claim there are no corrections, even exponentially small. So we will include in our discussion possible exponentially small corrections. And of course, there are observables that get wormhole corrections. I'm not making a statement that these observables only have small wormhole corrections. I'm asserting that these observables do not have wormhole contributions. So this will hopefully sharpen the puzzle, and then we'll get to the second part of the talk, which will be why then does anything show a sign? So if there's a large class of observables that show no sign of ensemble averaging, why does anything show a sign of ensemble averaging? In other words, there's no ensemble, and there's a large class of observables that don't receive wormhole contributions. Neither large nor small, they don't receive wormhole contributions. So why does anything appear to receive wormhole contributions? That'll be the second part of the talk. So I'm now going to tell you what are the observables that don't have wormhole contributions. And they're simply the energies or equivalently the dimensions delta I. Energies of states or dimensions of operators. Spins, Ji, and couplings. Of all states in the theory. Except I have to explain what I mean by all states in the theory. You take an integer k, I don't care, positive or zero, I don't care how big it is, 1,000,001. Then you take the 1,000,001th energy level. And I claim that the energy spins and couplings of that level and of every other level you might specify by an integer don't receive wormhole contributions. So we'll have to decide how to test this. We'll have to decide what calculation can do that involves wormholes. They could have shown us how to calculate a wormhole contribution to these observables. So, but I think once you formulate that carefully, it's fairly obvious what the answer might be. And it was, well, at the level of classical solutions and a little bit beyond it, it was proved in this paper.
But there's no n in these observables. So
They depend on n. Something I should have said is this. The spectrum has a large n limit in these things. I'm not telling you to take the limit though. These depend on n.
But I meant it's not an endpoint function, for example. Or could it be?
No.
The
If we're doing a 2D CFT, what I've enumerated here is a complete set of observables. In higher dimensions, that's not true. For example, in 4 dimensions, these observables wouldn't give you any easy way to determine the partition function on S2 times S2, which is a CFT observable in 4 dimensions. But in 2 dimensions, this is a complete set of CFT observables. So I'm claiming in some sense, all CFT observables are not affected by ensemble averaging. But obviously, there's some fine print there. So where's the fine print? If you take n large, keeping the energy above the ground state fixed, you get to the region studied by integrability, which is the region not affected by ensemble averaging. If, when you take a large n, you take the energy proportional to n or n squared, the details depend on the theory, then you get to the black hole region, and that is affected by ensemble averaging. So from these observables, there's no way to make statements about black holes. These are the observables studied in integrability. What do you say?
What about non-local observables, which are studied by?
I haven't really thought about them, but my guess is that anything that can be studied by integrability isn't affected by ensemble averaging. But it would be interesting to try to check that.
Suppose the black hole threshold is n, could you consider some energy which is n/2?
If we're below the black hole threshold,
Or you mean parametrically?
it's more
That's my
straightforward.
question.
3 dimensions is more straightforward than more than 3 dimensions. In 3 dimensions, it will be enough to be below the black hole threshold by any amount proportional to n. It's tricky in higher dimensions because there are small black holes. There's a Hawking page temperature, but there also are small black holes below that. So in above 2 + 1 dimensions, I will only say what I said on this blackboard. But in 2 + 1 dimensions, I think that being below the black hole, first of all, then there is a sharp black hole threshold. That's not true in higher dimensions. And as long as you're below it by a parametrically large amount, I think you'll be okay. Okay, so we want to find some observables which we can study by means of classical wormhole solutions. And then we want to, in that world of observables, generally one does see ensemble averaging. But we want to figure out in that world, what is there that we can express just in terms of the observables described in this, enumerated in this blackboard. And when we do that, we'll see that there's no ensemble averaging, or at least I'll tell you what we have to prove to see that. So as an example, we could take the genus 2 partition function. So I'm drawing on the blackboard a Riemann surface of genus 2. And when I draw it, the picture actually suggests a way to embed that Riemann surface in R3. And that suggests a 3-manifold whose boundary is the given Riemann surface, namely the interior. So the interior is a simple X, simple 3-manifold. With boundary are 2-manifold M. Now, let me tell you some interesting properties this X has. So I'm going to draw 3 circles on M. These are simple circles. They're not self-intersecting. They don't intersect each other. They're homologically independent. And in the X that's suggested by this picture, they each bound a disk. Now, there are infinitely many other ways we could draw through. You could make a mapping class group transformation of this Riemann surface. It would map these 3 circles to 3 other circles. Intrinsically, they'd be equivalent. They wouldn't be boundaries of disks anymore. So, in a little bit, we'll see why that's important. Now, sorry. I skipped a bit of background I should have reminded you about 2 + 1 dimensions. So in 2 + 1 dimensions, well, actually, let's just say 2-dimensional CFT. The ground state energy is minus C/12. And we're interested in large C. So the ground state energy is very large and negative. The black hole spectrum start at 0 energy. So the statements I've made, well, the original BTZ paper, they computed that the black hole spectrum started at 0 energy and that ADS3 itself had a negative energy. The interpretation of that as minus C/12 came later through the work of Brown and Noah and Strominger. Minus C/12 is something like minus 3L/8G. I might have the wrong constants. Where G is Newton's constant and L is the radius of curvature of the bulk theory. There's some formula like this, which is, well, the BTZ formula is reinterpreted by Strominger, Brown, and Hanel.
1/16, if you want to reference.
Without the 3?
Yeah.
Thanks. So, unfortunately, I have to use the middle blackboard because of the others aren't visible on Zoom. Suppose we calculate the partition function of this thing. Well, the partition function of any theory with a discrete spectrum, at least, is dominated by the ground state. So for large beta, it's asymptotic to e to the minus beta times minus C/12. And then there's a series involving the excitation energies of the higher states. But the important thing is that this grows exponentially for large beta. Not only does the ground state contribution grow exponentially for large beta, but the contribution of every state that's parametrically below the black hole threshold, in other words, all the ones that have negative energy by a significant amount, grow exponentially for large beta. And those are the only contributions that grow exponentially for large beta. So if we only knew how to calculate the partition function modulo terms that are finite at beta equals infinity, we'd be able to determine, let's say for n equals 72, some fixed value of n, forget large n. If you can calculate the partition function modulo an error that's finite as beta goes to infinity, you could learn the energies of all the states that have negative energy, but you wouldn't be able to learn anything about the states with positive energy. So what we're going to do is to look only at the part of the partition function that's exponentially growing. But then we have to also remember how we're going to calculate that part in ADS-CFT duality. So remember, I'll draw a more schematic picture. M is the boundary of some x. And we're going to, for today, we're going to assume that the theory on x can be approximated by Einstein gravity. There might be other light fields that wouldn't qualitatively change the picture. So in an asymptotic expansion for small g, the dominant factor in the partition function is the exponential of minus the action over g. Well, minus the action, which is something over g. So the action in Einstein theory has one part that anyway by itself is a multiple of the volume. But on shell, the Ricci scalar is also a constant. So that this term is also a multiple of the volume. So you'll find that the on-shell action of a classical solution of gravity in 3 dimensions is the volume over 4g L squared. There's a slight trouble with that statement, which is that in ADS-CFT, we're interested in non-compact 3 manifolds X, whose boundary is really this conformal boundary at infinity, where we define the CFT. That means that the volumes are always, in fact, infinite. But they're made finite by a renormalization, where you subtract a multiple of the boundary area. And after renormalization, the same is true. The renormalized action is the normalized volume over the same constant 4g L squared plus corrections. So it's important that although volumes are positive, renormalized volumes are not necessarily positive because we made a subtraction to define them. And we see that right away in this formula. So the partition function is exponentially growing. And the only way we're going to get an exponentially growing answer with a large coefficient proportional to c, which means 1 over g, is that the renormalized volume has to be negative. And in fact, for thermal ADS, see if we calculate this genus 1 partition function, the dominant contribution comes from a solution of Einstein gravity that I'll call thermal ADS. It's just a quotient of Euclidean ADS by an imaginary time translation with the period appropriate to the temperature we want to study. Then you find that the renormalized volume of thermal ADS is negative. It's minus beta times L over G times something. And we'll try to remember the constant, but the constant is the right one so that e to the minus, see, to make the duality work, what has to be true? Since the action is the renormalized volume over 4g L squared, what we want is that e to the minus the renormalized volume over 4g L squared should equal e to the plus beta times c over 12. So that's true. Thermal ADS has a negative renormalized volume, which is exactly right to reproduce this formula. That's not really a check on anything so far, because to some extent, that's how these formulas were determined. So, well, whether it's a check on anything depends on what else you assume you know. I don't want to say it is or isn't a check on something. It's a true fact anyway. So, but the moral of that story is that to get an exponentially growing answer comes because the normalized volume is negative. So now let's discuss something where we expect to get an exponentially growing answer. By the way, I want to stress this is an exponentially growing answer in beta. It might be small in n. Nobody's saying it's big in n. We're picking out the pieces that are exponentially growing in beta, regardless of how they depend on n. So let's try to find something that's exponentially growing in beta. Well, to do that, we could pinch. Well, hyperbolic geometers, as I learned in this project, refer to it as pinching, not terminology I was used to. You can pinch the circle, making it very small. So let me draw it so that it's been pinched. Well, at least draw a more pinched version. So now I've pinched that circle so that the circle is very small compared to the length of the tube passing through. Conformally, all that matters is the ratio of the two. You see, you can always calculate any amplitude, including this one, by summing over intermediate states, which here would mean the state that you observe in this little red circle. And what you'll get when you do that is going to be the exponential of minus beta, where beta is, well, this length if the circle has radius 1, or the inverse of length if beta is if length, it's the ratio of the two lengths. E to the minus, you'll get a contribution which is e to the minus beta times the energy of the state passing through that tube. Now, we know there are lots of states of negative energy, so we expect to get lots of contributions that are exponentially growing when beta is large. Where can we get them from? Well, the only way to get them is we have to get exponential growth when beta is large, means that we need to have VR negative if beta is large. Well, we really want to have VR negative and of order beta, of order minus beta, because we want not just exponential growth, but the exponent is supposed to be beta. So most 3 manifolds will not give a negative or normalized volume when you pinch them, but there are infinitely many that do. And if all we ask is that the normalized volume is negative when we pinch that particular circle, then in fact we will get apparent ensemble averaging. That won't be enough to kill wormholes with disconnected boundary. And we shouldn't expect it to, because if all when we pick out exponential growth in this channel, we're insisting that the state going through here isn't a black hole, but there can be black holes propagating on the left and right. So we have to describe an amplitude that doesn't involve black holes at all before we're not going to see what's characteristic of black hole physics. So what do we do? Well, if I label these circles A, B, and C, we simultaneously pinch A, B, and C. And the behavior we look for, now there are 3 betas. And we look for exponential growth in any of the 3 betas. So we're going to, in the tri-pinching region, we're going to get exponential growth with the sum of 3 exponents if the energies are all negative. So let me say about it. We want to isolate contributions that do show exponential growth when any of the 3 betas is large. That means we want, what manifold can give such a contribution? What can give such a contribution is a manifold X, which has the property that the normalized volume is negative whenever we pinch this, this, or this. Well, in our paper, we have a more complete explanation of various things. But for this precise question, which is what can be X such that its renormalized volume goes to minus infinity if you pinch A, B, or C, the answer is there is only one such X among classical solutions of Einstein's equations. So the only X is the one suggested by the picture. So, well, in general, if you pinch a circle, the renormalized volume goes to minus infinity if and only if that circle bounds a disk in the 3 manifold. Here we want to get the actual volume to go to minus infinity in each of 3 limits. So each of 3 circles should bound a disk. And as I explained before when I drew the picture at first, for the obvious 3 manifolds suggested by the picture, it is true that each of those 3 circles bounds a disk. And what's shown in our paper is that the unique solution of Einstein's equations where each of the three circles bounds a disk, is the obvious one suggested by the picture. In particular, it has a connected boundary, so it doesn't show wormhole contributions. So how would we describe the piece of the partition function that grows exponentially in each of three channels? Well, you get that by summing over all states that have negative energy. And then we have this exponential factor. Let's call this I, J, and K. And then we have a trilinear coupling of the three states, or the corresponding vertex operators. See, if you're summing, in general, you could calculate this amplitude by summing over states propagating through the three channels. For fixed states propagating through the three channels, the boundary, if you cut on all three circles, you see two three-hole spheres. And the partition function on a three-hole sphere is a trilinear coupling lambda ijk of the three vertex operators. So, well, if we didn't restrict the energy to be negative, you have an exact CFT formula, but the genus 2 partition function can be written like this. If we only want exponentially growing pieces, that means we only want the parts where the energies are all negative.
I have a trivial question. If I
Yeah.
break it into, can you hear me?
That's,
Yeah. If you break it to two whole spheres, then at least naively it's lambda Ij times lambda Jj, lambda Kkj.
you're right. That is correct. For the picture I actually drew, we got this. We could have drawn another picture that would have given what I wrote. If we want to get lambda ijk squared, let me just draw the appropriate picture that gives that. This is again meant to be a genus 2 Riemann surface. I hope you can understand the picture. So again, I've drawn through, well, actually, now I've drawn an inequivalent set, actually, of three independent circles. And everything I said could have been said for this picture, and maybe it would have been better. And then it would have given lambda ijk squared instead of what actually comes from the picture I did draw. I wonder if it's wrong in the paper. I need to check that. The paper, I don't know, but the paper might have the same mistake that you just pointed out. Maybe it's stated in such a way that it's not really wrong. Any other questions?
Is it important how you define the renormalized volume? Because like you're making a choice that you're putting probably the boundary on a hyperbolic metric. In general, the renormalized volume depends what boundary metric.
It's actually not important. Well, what Lorenz is pointing out is that the CFT partition function has a conformal anomaly, so it's not a completely well-defined number. So to state this more precisely, we could do the following. First, we should pick a metric such that we do expect the formula to be of this form. What is that metric? The metric should be flat in the three tubes. Didn't plan on drawing this very well, but where when the circles we're pinching, they should lie on flat tubes. I won't flatten this one. And then beta is the length of the flat tubes. There isn't any canonical choice of what there is away from the three tubes. And exactly what you mean by these couplings, lambda, ijj, and so on, depends on exactly what you do there, but it's not important in the argument. Is that satisfactory?
Yeah, thanks.
I'm still not clear about my question. So we can consider the same manifold in two separate limits, the one which is in the lower left and the one which is in the upper right.
Yeah.
And we can interpolate between them with the same three manifold in the interior. So is there a statement about what happens throughout the interpolation, or is it that you're only interested in the two limits?
Well, I'm only making assertions about what happens in this type of limit where there are three long tubes. I'm only making an assertion about terms in the partition function that grow exponentially in any of three limits. And the three limits could be those suggested by this picture or those suggested by this picture, which are indeed two independent things we can do. In higher genus, there would be more than two. Does that answer the question?
Yes, but the thing is that if I think of it as a problem in conformal field theory, the fact that we have these limits, different limits, usually it's the case that with a little bit more information, you learn a lot about what's going on in the interior because it's.
So if we're naive, we'd think that, as I told you, all the states are subthreshold states in the large N limit. And I'm claiming all of the, so therefore, roughly speaking, I've claimed that couplings and dimensions, spins, and couplings of all the states aren't affected by ensemble averaging. So then you'd ask, why isn't there an immediate contradiction? Doesn't that prove that the whole partition function isn't affected by ensemble averaging? Doesn't work that way because there's a singular interchange of limits involving the Hawking-Page phase transition. And you can't really extrapolate easily between the two limits. But by the way, the three manifold that contributes here is not the same as the one that contributes here. So there's one three manifold that is negative normalized volume in this picture. There's a different three manifold that is negative normalized volume in this picture. So the one that contributes to one limit simply doesn't contribute. The one that contributes exponentially growing pieces in one limit doesn't contribute exponentially growing pieces in the other limit. See, I think the essence of it, Maddie, is that these observables that are accessible by integrability only give a partial CFT, and you can't complete it to a complete CFT without, well, roughly speaking, including the black holes. We might come back to that more precisely later. Any other questions?
We're assuming that the wormhole contributions are solutions.
Well, I've analyzed the case of solutions, but of course, we don't actually believe that everything comes from solutions. It's just that non-solutions are harder to study. But there is one example where it's strongly believed that non-solutions are important. So that's the spectral form factor where you allow beta to be complex. Well, you could take two complex betas. They don't have to be complex conjugates. But a nice case is that the two betas are complex conjugates. That's the spectral form factor. And it's claimed that it receives a contribution. It's claimed that to be compatible with chaos and black hole physics, in some sense, it should have a contribution that's suggestive of wormholes. And the literature contains a plausible proposal by Cutler and Jensen. They looked at the topology T2 times R with two boundaries. And there's no classical solution, but they tried to do the path integral anyway. They got something. I can't promise what they got is correct, but what they got is completely consistent with what I'm telling you. It has no exponential growth in any limit. So to the extent that people have tried to look at non-solutions in the literature, they got results that are completely in accord with what I'm saying. I can't say more than that. There isn't a systematic theory of non-solutions.
I mean, one might imagine non-solutions, which are a little tiny cube that goes from connects to partition functions. So the things you're computing. But yeah, I mean, this is a mathematically clear statement. But
in principle, it's also conceivable that if you take even solutions, but since they're infinitely other solutions, is it clear that if you resum all of them, that you don't get something exponentially growing?
Well, let me give a more intuitive reason rather than the proof in our paper that the subthreshold states only come from an X, such that each circle bound to disk. The sub-threshold states come from small perturbations around ADS. And that means that space is like ADS2, the boundary is the boundary of the disk. So if you want to see those states, you should see in this channel something that has the right topology. And what we proved, if you like, is that the renormalized volume becomes negative if and only if the topology is in accord with what I just said. So you can look for trouble, but I think that I'll just say that response to one with the previous question. One can look for trouble, but both the classical solutions and what's known about path integrals with non-solutions suggest the interpretation I'm giving. Actually, there's something I had meant to say that I forgot about. I was reminded by this Cutler-Jensen thing. Let me give you the simplest example of a wormhole. The simplest example of the classical solution. You take M to be of genus at least 2, and then you take a metric on M that satisfies the 2-dimensional Einstein equations, R equals -2. And then there's an easy solution in 3 dimensions. This obeys Einstein's equations in 3 dimensions. And it's a wormhole with 2 asymptotic boundaries. One at t equals plus infinity, one at t equals minus infinity. It has the property that no circle is the boundary of the disk, because no circle in the boundary that isn't already a boundary, no non-trivial circle in the boundary down to disk inside, because since it's just a product, R times sigma, topologically it's contractible into sigma. So you can't do anything interesting topologically by using the R direction. So a special case of what I've told you is that its normalized volume never goes to minus infinity. But you can easily check that by hand. This metric is so simple that you can easily calculate the normalized volume, and you'll quickly find that it's a topological invariant that only depends on the genus. In particular, it doesn't go to minus infinity. So this wormhole contributes to amplitudes with black holes running around the loops, but not to amplitudes with states below the black hole threshold running around the loops. Any other questions? Yes?
You want to exclude the case where you have punctures on the boundary for some reason?
No? What do you want to ask about it?
That you could also consider a 3-punctured sphere times interval.
We can, but it's hard to make sense of. I'd like to discuss it, but well, first of all, it's a non-solution. So we'd maybe have to imitate Cutler and Jensen or something. But there's a more fundamental problem, which is that any such metric, you could make an SL2C transformation on the left, which doesn't extend as a symmetry of the whole manifold. So it would be a symmetry of your calculation, but those are the true moduli in the path integral. So whatever, it looks for that trivial reason that whatever you compute will be 0 or infinity. But I think it would be interesting if anyone would want to try to get an answer other than 0 or infinity for such a thing. The coefficient of the infinity would be this. Because where the infinity would come from, you make a conformal transformation. Your infinity and moduli space, the 3 points are very close together. And it will just factor, the coefficient of infinity will be this. So any obvious calculation you can do will give either 0 or infinity times the answer you already had before. But I can't say more than that. Yes.
I don't understand the previous example, because what is the claim? I mean, you cannot pinch just like in the product with R. What is the claim? Because you cannot pinch like one.
This is a good point, and I tried to shorten that explanation. So for this family of metrics, the metric is the same when both components are infinity. So you can't pinch one independent of the other. You can pinch them both together, and then you'll see the normalized line goes to minus infinity. I knew this example, it was part of my motivation, but I was wondering what happens if you just pinch on one side. Not being able to answer that is why I eventually consolidated a math operator. So existence theorems show that there is a classical solution where you vary the two complex structures independently. And therefore it is possible to pinch one without the other. But there's no explicit formula. So the general theorem shows that the normalized volume doesn't go to minus infinity, but you can't show it by an explicit calculation. You feel like it's a non-trivial illustration of the general theorem. So, okay. So now we got to the final question. Why is anything affected by apparent wormhole averaging or apparent ensemble averaging? In other words, there's no ensemble, and there are lots of observables that don't appear to be affected by ensemble averaging. So now we should zero in on the question, why do some observables appear to be affected by ensemble averaging? Well, those are observables involving black hole states, so we have to discuss something that's special to black holes. And I claim there are two relevant things. The first is that black hole physics is chaotic. As shown by Stanford and Schlenker a number of years ago, following it Hooft and reinterpreting earlier work of Dray and Hooft. So this fact is very well known in discussions of this subject. The black hole chaos in black hole physics was part of the motivation that led eventually to the work on JT gravity as an ensemble average. A second fact, which is possibly slightly less appreciated, is that the black hole spectrum and couplings do not have a large n limit. This isn't something that's as clearly established as the first one is, but I think if you think about it a little bit, you'll start suspecting it must be true. The size of the black hole physics is sort of size of the black hole Hilbert space at a given temperature set, or in a range of energies appropriate to a given temperature, is e to the s, which is something like e to the n squared. So if you compare n equals 10 to the 6 or n equals 10 to the 6 plus 1, the Hilbert space is much bigger. In that example, Hilbert space grows by a factor of e to the 2 times 10 to the 6. So, except for an insignificantly small fraction, almost all states in the Hilbert space are new whenever you just increase n by 1. So it's extremely hard to see in what sense the black hole spectrum and couplings could have a large n limit. And there's certainly no proposal in the literature for such a limit. By contrast, the thermal field double state of an entangled pair of black holes does have a large n limit, as shown by 1. Right? That's true for large n gauge theory in general, but in ones with gravity duals, it has a description in terms of an entangled pair of black holes. What I said about large n is exactly analogous to the standard claim about large volume in quantum statistical mechanics. So the Hilbert space in which you do quantum statistical mechanics for finite volume does not have a large volume limit. What textbooks do is calculate the thermodynamic functions at finite volume, and then they observe that the thermodynamic functions have a large volume limit. They take the large volume limit of the thermodynamic functions, not of the underlying Hilbert space, which does not have a large volume limit. That's why rigorous people in statistical mechanics, Haag, Hugenholtz, and Winnick, introduced the thermofield double in the 60s because it does have a large volume limit. So it provides a framework where you can study the large volume limit of statistical mechanics in the Hilbert space. Analogous to the fact that in the black hole case, the Hilbert space of a pair of entangled black holes has a large M limit or a small G limit. But for a single black hole, it's more like a single statistical system. I presume there's no large M limit. I'll try to convince you that everything makes sense if we assume there's no large M limit. Now, when I say there's no large M limit, that's a slightly vague sense because I didn't say in what's, I didn't try to say in what sense there isn't a large M limit. It's hard to imagine a sense in which you would hope there would be a large M limit because the Hilbert space grows so drastically whenever you change n by 1. But I really mean that there's no unknown regularity of black hole physics for large n. So there's a lot of known regularity. So what is known regularity? Well, the most obvious is that the entropy is a smooth function of the energy in n, and maybe other charges to throw in. That's the most familiar regularity. Something else which I believe is true, and there are a lot of results in this direction, but they tend to be results that hold for formulated so that they hold for arbitrary CFTs without fully exploiting what would be true when you have gravity dual. But there are nice results for things like the average value of lambda ijk squared for states in a particular band of energies. So this has a smooth average. And these things vary to what extent they've been discussed in the literature, but there are lots of averages you can write down that work very plausibly, have smooth averages. So when I say the known regularity of black hole physics, I mean a lot of things that are known or have been, or in some cases haven't yet been analyzed, have a regular behavior for large n. But we want to imagine that that's the only, that there's no undiscovered, no fundamentally undiscovered regularity in black hole physics for large n. So if that's true, let Hn be the black hole Hamiltonian. At some n for some range of temperatures, the energy appropriate to some temperature. Well, chaos means Hn is a pseudo-random matrix. But lack of regularity for large n means that the Hn of different n are independent pseudo-random matrices. So if you could calculate exactly the black hole Hamiltonian when n is 1,000,001, it would look like a pseudo-random matrix. And if you could calculate it when n is 1,000,002, it would look like an independent pseudo-random matrix. Well, nearly independent. It's easier to explain what I want to say if I assume that the Hn for different n are independent draws from a pseudo-random ensemble. But you can actually argue that they're only exponentially close to being independent. I'd like to postpone that though for a moment. accepting this statement that HN is a pseudo-random matrix, and for different n, you get different draws from an ensemble. Consider, well, the most important example is the partition function, but more generally consider any observable that only depends on HN. Well, we want to calculate the expectation value of W, let's say. Well, we now should ask, is W self-averaging in random matrix theory? If W is self-averaging in random matrix theory, that means that for different values of n, for every value of n, we have an independent draw from the pseudo-random ensemble, but the draw doesn't matter very much for a self-averaging quantity. So if W is self-averaging, then its dependence on n will be smooth. And we might be able to calculate that dependence on n with known methods. Even if that's the case, there will be exponentially small corrections that are erratic in n. And we don't expect to be able to calculate the erratic corrections with known methods. But at least if W is self-averaging, it'll have an average behavior that's smooth, and we might be able to calculate it. Suppose, on the other hand, W isn't self-averaging. Well, if W isn't self-averaging, we definitely can't calculate it with the gravitational path integral with any known method. So, therefore, the observables we can calculate with known methods are the ones that are self-averaging in random matrix theory. That's the basic reason gravity is connected to random matrix theory. There's chaos. When you change this constant slightly, you have chaos and a slightly different draw from a random matrix ensemble. And since you only can calculate things that depend on Newton's constant smoothly, and those are the things that are self-averaging, therefore gravity appears to be connected to random matrix theory. Whatever you can calculate is something you could have calculated in random matrix theory, in an appropriate random matrix ensemble. Whether something is self-averaging or not, it might have an average. If something is not self-averaging, that means it has large fluctuations. There might be large fluctuations around the non-zero average. If that's the situation, we might be able to calculate a function that would give us a smoothed average value of W. We wouldn't be able to calculate the wild corrections with known methods, with the gravitational path integral.
I guess we would be able to calculate the square of the.
Well, we might be able to. So let's discuss the square. Whether or not W has a non-zero average and whether or not W is self-averaging, the product of two W's might have an average. It might be self-averaging, but even if it isn't self-averaging, it might have an average. If it has an average, we might be able to calculate it with the gravitational path integral. So, now I'm taking the connected thing, because the connected thing is meant to be an average over nearby values of n, which is very large. But I want to stress that we're not averaging on purpose. We're trying to calculate for a definite value of n. But the theory can only give us smooth functions of n if all we do are semi-classical calculations. And the best a semi-classical calculation can be, in the case of an erratic function, is some kind of smooth interpolation. So connected means that you average this over nearby values of n. So it's not manifestly zero, but anyway. So what we could conceivably calculate with the gravitational path integral is a smooth average, a smooth approximation to the product of any collection of observables. Now, these somewhat abstract considerations don't tell you how to do the calculation, but there is an obvious hypothesis. the obvious hypothesis is that trace e to the minus weight h corresponds to a boundary, which is a circle times a sphere. Where the circle has circumference beta. And if you have n of them, you've got n of these manifolds. The obvious hypothesis is that the wormhole computation with a connected X that has these n boundaries is giving us some kind of smooth approximation to the product of the K observables. The product of the K observables may or may not be a smooth function of n. Well, in random matrix theory, it can't be completely smooth. Every observable has erratic exponentially small terms that depend on the specific draw. But it might be a smooth function of n modulo small corrections, or it might not be. But either way, the hypothesis is that what the gravitational path integral is giving us is a smooth approximation to that function.
Would you think that something like the connected part of an n-point function for large n is an example of something which has, it might be very small, but with large fluctuations?
So you want to calculate.
That's one of the super naive things that people would say, how effective field theory breaks down in black holes. You ask for a 1/g Newton point function should deviate from effective field theory at order 100%, even though it's very tiny, but it would deviate from effective field theory at order 100%. Is that the sort of thing that you think would happen?
Well, it might. So one asked me about operators with dimensions of order n, but below the black hole threshold. But if you had enough of them, if the dimensions are big enough, if you take n large, but an individual operator has a dimension of n squared, you're not in the regime I'm talking about. If you take n large with n squared operators, each with low dimension, that might be similar. I don't have anything to say about it, but it definitely might be a different regime. So there's one more thing I should tell you, because here I only talked about observables that only depend on the Hamiltonian. But that's a little bit artificial, especially in higher dimensions. So that forced me to take the boundary manifolds to be a product of a circle times a sphere. But what if the boundary manifold is something else? So the trouble is that then we have to do random CFT rather than random matrix theory. And random CFT is, of course, much less understood than random matrix theory. So I'll say what I think it must be true by process of elimination, but I wouldn't have suggested it otherwise. So to describe a CFT, well, what I'm going to say is either a complete description in 2 dimensions or a partial description above 2 dimensions. To describe it to CFT, we give the energies or the dimensions, the spins, and also the couplings. Now, the energies and the dimensions we can think of as being contained in this pseudo-random matrix, the Hamiltonian. But how will we interpret the couplings? Well, first of all, the couplings aren't arbitrary numbers. They're constrained by crossing relations. And the crossing relations are very powerful. And we believe if we do the complete solution of the crossing relations, we learn that there's no ensemble. There's only one CFT for each n or whatever. And if we, with the right supersymmetry, and if we assume the wrong energies, there won't be any. That's what we believe, at least. But that's the exact statement. Suppose we only understand the crossing relations in the same approximation in which we're doing the gravitational path integral, which means we're seeing terms of order e to the minus n, but we're not able to set n to a definite integer, like 10 to the 6 plus 1. Let me make an analogy with the S matrix of relativistic field theory. We believe that relativistic unitary S matrices are very special. They correspond to quantum field theories that actually exist. But there's a vast swampland of effective field theories that make sense order by order in a low energy expansion to all orders. You can take, with mild restrictions, you can take more or less arbitrary coefficients of all the operators appearing in the low energy effective action. So there's a vast swampland of effective field theories. And in that swampland, there are very special points that are unitary relativistic S matrices. So here I imagine that there's a vast swampland of effective solutions of the Gaussian relations. And for each n, you have a pseudo-random CFT. For each n, you have a highly non-random CFT. But what it looks like in simple measurements, like the computations we're able to do of a product of k partition functions. In simple measurements, the pseudo-random, the exact CFT looks like a random draw from an ensemble, a swampland ensemble of effective CFTs. So then I'd say everything, for the case of a general manifold, I'd say everything I said before, but with pseudo-random CFT replacing pseudo-random matrix. I guess that's it for today. Yes.
So the bulk knows that n is quantized,
Yes,
right? Because it's the flux through some place surface and it knows about that.
Yes.
I feel like that feels not inconsistent, but slightly in tension with what you're saying that the bulk.
It's not intention at all. The Hilbert space only exists when n is an integer. So
Yeah.
the bulk only has a Hilbert space when n is an integer. These computations don't know that n is an integer.
Okay.
Let me say something slightly different. I'll phrase it slightly differently from the way I did in the talk, but perhaps it will be clarified. I believe the concept of black hole microstate is ill-defined except for BPS states. Because to call something a black hole, you need causality, which is valid at n equals infinity or in an asymptotic expansion near n equals infinity. But to have quantum microstates, you need n to be an integer. So the two are not simultaneously present. Except for, with the exception of the BPS spectrum. The BPS spectrum is where you do have black hole microstates.
They're also growing within. I think your point is about how things interface with the large and limit.
It's true that you, I believe, could ask questions about the BPS spectrum that would probably show similar properties. Unfortunately, there aren't couplings. I don't think BPS spectrum has a large n limit. Let's say when it's going within, that's true. That's why it's in it.
Yeah.
But that is the
People
case.
talk about black hole microstates. They're imagining the Newton constant to be finite.
Yeah, it approximately makes sense. It's like trying to specify position and momentum. You can specify position and momentum approximately, but sometimes they run into trouble if you don't take into account that you can't specify them both exactly.
But we can specify n precisely in the bulk. So, I mean, it was
We can.
saying.
Yes, we can.
So we could be considering a theory with definite n. I think what you're saying is we can consider the theory with definite n, and we change from n to n+1, and the results we calculate using the bulk would be smooth functions of n.
The results we calculate with the gravitational path integral, but we believe in the exact theory somewhat. Some observables are erratic. So one simple statement was that the observables that behave smoothly with them are the ones that are self-averaging. Well, and all I said was that
I mean, it's important that you're not saying that this average we have comes from averaging over n.
no, definitely not.
Because
No.
that's a common misconception of it.
Yes. I know. I tried as hard as I could. I tried as hard as I could to formulate this talk in a way that wouldn't draw anyone to misconceptions of that nature.
Okay, yeah, but
So if we do, the BPS calculations where they're able to get an exact integer number for the number of microstates at a given n, why would you say that's possible for BPS states, but you wouldn't think it's possible for black body?
Well, the question was well defined for BPS states.
Yeah. So it's about the fact that you don't have chaos, that it's just some actual exact degeneracy.
I'm not totally sure there isn't chaos, but there is a correct definition of the Hilbert space. Whereas if you aren't in the BPS limit, the combined system has a Hilbert space. You could do that. In ADS-50, you could, without claiming the state as a black hole, it makes sense to talk about the energies of all the states.
Yeah.
Some are
Can you get
informally,
that with the bulk part integral or some bulk calculation?
not with the calculations we know how to do now. I don't have any objection in principle to being able to do that. Well, the problem I posed was, why is it that we get apparent ensemble? The question I posed was how to interpret the answers we get from the calculations we actually know how to do.
But let's see, the objection in terms of defining the Hilbert space in terms of the growth in dimension, that you also have for the BPS state. So perhaps you
For
want
a
to
large
say-
n calculation.
I do not claim that the BPS Hilbert space has a large n limit. I imagine it does not.
So the differences between calculations that work at fixed n and calculations where you're doing a semi-classical expansion. What the two?
That's a difference. Yeah, but for the I would say that for the BPS states, it's well defined to call them black holes.
Yeah.
For other states of finite n, it'll be approximately correct to call something a black hole, but because it's only approximately correct, you can't expect to make exact statements.
But I'm not sure what's the difference. So maybe one difference is perhaps that when you specify the range of energies, you have to be very careful. But I mean, in both cases, n is finite. If n is finite, then finite entropy in both cases. I mean, I have the feeling is that because we can calculate it for BPS states, you say that. But I think this type of reasoning would have said that also for BPS states, we wouldn't be able, for example, to get the integer degeneracy.
No, I didn't say I'm not saying what we can or can't calculate. I'm trying to say what's well defined. Take the 1 millionth state in 2 + 1 dimensions and follow it as a function of n.
Yeah.
When n is much bigger than a million, we say it's not a black hole. When n is much less than a million, we would say it is a black hole. But there can't be a precise statement there, obviously, because you don't.
I'm not sure. Wait.
There's no. Not only is there no objection, I'm not saying that you wouldn't in principle be able to calculate the energy of the 1 millionth state. I'm sure at least by computer you can in principle.
But I mean, the one thing that is special about the BPS states is that they have the minimum energy, right?
Yeah.
So then I could also specify in the non-BPS case the states within some band of energy previously.
Yeah.
Pick some band of energy and then we.
It's well defined to specify that and well defined to try to calculate it.
Right.
And it can be done by computer. The only part that I think isn't truly well defined is to claim that they're black holes. I think that that's only precise in the large n limit.
Why do you say it's precise whether a BPS state is a black hole? Because I can change the dilaton and they'll stop it in black hole, right? Be some.
What do you mean by changing the
If I change the the coupling of my theory, I can change G, take lambda down to really small, and then I'll go.
I feel you might be able to argue that the BPS states. You might have simply said the following: how would you decide that a BPS state is a black hole? You have to probe it, then it's not BPS anymore. So you might claim that that's a reductio ad absurdum of what I was claiming.
I think you can. I mean, you can do other things like calculate the expectation values of operators in those BPS states.
Yeah, I know.
So, I mean, you could also take the position that you could also make the statement that one particular BPS state would not be black hole. The black hole has something to do with the superposition of elements.
Well, what I really wanted to say though was for the non-BPS states that for microstates are well defined for finite n. But I do not believe that the statement that a microstate is a black hole is truly precise for finite n.
Can I ask, what would you mean by a black hole of mass 5 and Planck? It's decaying almost right away. I mean, what does a black hole of mass 5 and Planck mean? So if there's going to be a formula for its entropy, it'll be a function of that number 5.
I think for this discussion, it's better to think about the black hole in ideas. So it's
Okay. Okay.
Anyway,
I mean, if it's 5M Planck, then it's still unstable even in ADS, presumably, right?
Well, I mean,
Yeah, yeah.
it's better to talk about stable black hole.
Was your comment about the smoothness in N of the gravitational computation on from the gravitational path integral only meant to be to apply to saddle to like the semi-classical expansion around saddles, or was it also meant to apply for the non-saddle solutions? So the Scotland-Jensen formula is independent of N, actually. So it's a smooth function to N, but it's not clear to me whether that's supposed to be true.
well, I don't know what will be done in the future. I've tried to find calculations that wouldn't depend smoothly on n with no success. It was only a comment on what we know how to do.
But you don't know of any argument, like there's no abstract argument that would ensure that. Whereas expanding around the classical saddle, obviously there would be something that would function.
For BPS sake, we can discuss the whole sum, so as to get an integer.
Yes.
So that's an example of something that could be good as something that doesn't depend so much.
I actually want to look at that and see whether there's anything that's computed exactly that depends erratically on it. I think that would really be interesting if there is.
Yeah, well, you get integers for each n. Well, I don't know. Yeah, maybe it's a simple function of n.
I don't think it's going to be too simple because the coefficients of non-different functions and stuff like that. But well, it would be really interesting if there was anything you could compute exactly that in some sense was sensitive to chaos.
Yeah, well, this is not. I don't think. Yeah, this is a different. Yeah,
Sensitive.
I don't think it's chaos. It's not the same as the.
Well, anyway, since it is gotten by summing infinitely many contributions, it might do something that other calculations don't do.
Yeah, in some sense, you get something which has a precision which is e to the minus s compared to the leading order is e to the s, right?
Yes.
Then you get something which is 1, or I mean, it has some
Yeah.
integer value